Download this code from codegive.com, link in the description below. OK, let's dive deep into benchmarking rocksdb key value workloads, especially focusing on techniques used at Facebook. Although I don't have internal Facebook code, I can provide a strong simulation based on public knowledge and best practices. This will be a comprehensive guide covering setup, benchmarking tools, workload generation, result analysis, and code examples. Table of Contents *. 1. Introduction to rocksdb and benchmarking. *. What is rocksdb? Its key features and use cases. *. Why benchmark rocksdb? Performance goals and common metrics. *. Facebook's use of rocksdb and its importance. 2. Setting up your environment. *. Installing rocksdb and necessary dependencies. *. Configuring rocksdb options, crucial for realistic benchmarking. *. Hardware considerations, CPU, RAM, storage. 3. Benchmarking tools, FIO, ycsb, and custom tools. FIO, Flexible I/O Tester Low-Level Disk I/O Benchmarking. Use cases for rocksdb. ycsb, Yahoo Cloud Serving Benchmark Standardized Key Value Workload Generator. Configuring ycsb for rocksdb. Custom benchmarking tools. When and why to create your own tools. Briefly mention, db_bench, rocksdb's built-in benchmarking tool. 4. Workload generation and modeling. Understanding workload characteristics, read/write ratio, key size, value size, access patterns, uniform, Zipfian. Using ycsb to generate realistic workloads, example configurations. Creating custom workloads to simulate specific application scenarios. 5. Code examples, C++ and Python. Basic rocksdb interaction, C++ opening, writing, reading, deleting. FIO configuration examples, text example FIO job file for sequential and random I/O. ycsb configuration examples, text example ycsb property file for rocksdb. Python script for automating benchmarking, Python example script that runs ycsb or custom workloads and collects results. 6. Running benchmarks and collecting data. Preparing rocksdb for benchmarking, data loading, compaction. Executing FIO, ycsb, and custom benchmarks. Capturing relevant metrics, latency, throughput, CPU usage, disk I/O, memory usage. Tools for data collection, perf, IOTop, vmstat, rocksdb statistics API. 7. Analyzing results and tuning rocksdb. Understanding the impact of rocksdb configuration options on performance. Using data visualization, graphs, to identify bottlenecks. Tuning rocksdb parameters. Block cache size. Write buffer size. Compaction settings. Bloom filter configuration. Iterative tuning process. 8. Advanced benchmarking techniques. Benchmarking with different storage devices, SSD, NVMe, HDD. Benchmarking with simulated hardware failures, example disk latency injection. Benchmarking with concurrent workloads, multiple ycsb clients. Benchmarking different rocksdb versions. Benchmarking in Docker containers. 9. Facebook's rocksdb usage, lessons learned, hypothetical. How Facebook likely uses rocksdb in its infrastructure, caching, metadata storage. Asterisk workload characteristics specific to Facebook's use cases, scale, read heavy versus write heavy. Asterisk tuning strategies Facebook might employ to optimize rocksdb performance. 10 Conclusion. 1. Introduction to rocksdb and benchmarking. Asterisk What is rocksdb? Rocksdb is a high-performance embedded key-value store. It's a fork of LevelDB created by Facebook, designed to handle write-intensive workloads and large-scale data. Key features include asterisk log structured merge tree, LSM tree, architecture, optimized for high write throughput. Asterisk write-ahead logging, while ensures durability. Asterisk support for various storage media, SSD, HDD, NVMe. Asterisk pluggable compression algorithms, Snappy, ZSTD, etc. Asterisk highly configurable for different workloads. Asterisk wide range of data types including column families. Asterisk why benchmark rocksdb? Benchmarking is essential for asterisk understanding performance. Asterisk determine how rocksdb performs under specific workloads. Asterisk identifying bottlenecks. Asterisk pinpoint areas where rocksdb is underperforming, CPU, disk I/O, memory. Asterisk optimizing configuration. Asterisk find the best rocksdb settings for your application's needs. Asterisk hardware selection. Asterisk evaluate the suitability of different hardware configurations for rocksdb. Asterisk regression testing. Asterisk ensure that code changes don't negatively impact performance. Asterisk Facebook's use of rocksdb. Asterisk Facebook uses rocksdb extensively in its infrastructure. It is likely employed for asterisk caching. Asterisk storing frequently accessed data in a fast, persistent layer. Asterisk metadata storage. Asterisk managing metadata for various services. Asterisk time series data. Asterisk handling time series data in certain applications. Asterisk social graph data. Asterisk potentially storing relationships and connections within the social graph. Consider the write-heavy nature of social network updates. Asterisk message queue backend. Asterisk storing messages for asynchronous processing. Facebook likely requires extremely high throughput, low latency, and massive scalability from its rocksdb deployments. They would have developed sophisticated benchmarking and monitoring tools to ensure optimal performance under heavy load. Key performance goals and common metrics. Asterisk throughput. Asterisk the number of operations, reads, writes, per second. Measured as ops/section. Asterisk latency. Asterisk the time it takes to complete a single operation, read, write. Measured in milliseconds, ms, or microseconds, s. Asterisk CPU utilization. Asterisk the percentage of CPU resources used by rocksdb. Helps identify CPU-bound bottlenecks. Asterisk disk I/O. Asterisk the amount of data read from and written to disk. Helps identify I/O bound bottlenecks. Asterisk memory usage. Asterisk the amount of RAM used by rocksdb, including block cache. Asterisk write amplification. Asterisk the ratio of the amount of data written to disk to the amount of data written to rocksdb. A key metric for LSM tree-based databases. Lower is generally better. Asterisk space amplification. Asterisk the ratio of the amount of disk space used by rocksdb to the amount of data stored in rocksdb. Asterisk compaction score. Asterisk a measure of the amount of compaction work pending. High compaction scores can indicate performance problems. 2. Setting up your environment. Asterisk installing rocksdb. Asterisk Linux, Debian/Ubuntu. Asterisk Linux, Red Hat /CentOS/Fedora. Asterisk Mac OS. Asterisk Python. Asterisk configuring rocksdb options asterisk this is critical for realistic benchmarking. You need to tailor the configuration to your expected workload. Here are some key options to consider, using options class in C++ or Python. Asterisk create underscore if underscore missing, create the database if it doesn't exist, usually true. Asterisk error underscore if underscore exists, throw an error if the database already exists, usually false. Asterisk wal underscore dir, where the wal files are stored, important if you have a separate, faster drive for wal. Asterisk max underscore background underscore compactions, number of background compaction threads. Increase for write-heavy workloads. Asterisk max underscore background underscore flushes, number of background flush threads. Asterisk write underscore buffer underscore size, size of the in-memory write buffer, before flushing to disk. Larger buffers can improve write throughput. Asterisk max underscore write underscore buffer underscore number, maximum number of write buffers. Asterisk target underscore file underscore size underscore base, target size of each SST file. Asterisk level 0 underscore file underscore number underscore compaction underscore trigger, number of L0 files that trigger compaction. Asterisk max underscore bytes underscore for underscore level underscore base, maximum total size of level 1 files. Asterisk max underscore bytes underscore for underscore level underscore multiplier, multiplier for the maximum size of each subsequent level. Asterisk block underscore cache underscore size, size of the block cache, for caching data read from disk. Increase if you have a read-heavy workload and sufficient memory. Crucially important. Use new LRU cache to create the block cache. Asterisk compression, compression algorithm to use, example K-snappy compression, KLZ4 compression, KZSTD compression. K-no compression for disabling compression. Asterisk compaction underscore style, the compaction style to use, K compaction style level, K compaction style universal, K compaction style FIFO. K compaction style level is the most common. Asterisk bloom underscore filter underscore policy, add bloom filter to each SST file. Useful for reducing disk reads for non-existent keys. Use new bloom filter policy. Asterisk hardware considerations asterisk. Asterisk CPU asterisk sufficient cores to handle the load. Pay attention to single core performance as rocksdb does a fair amount of single-threaded work. Asterisk RAM asterisk adequate RAM to accommodate the block cache and other memory structures. More RAM generally translates to better read performance. Asterisk storage asterisk the most important factor. Asterisk SSD/NVMe asterisk essential for high-performance workloads. NVMe drives offer the best performance for latency-sensitive applications. Consider enterprise-grade SSDs for reliability. Asterisk HDD asterisk suitable for read-mostly workloads where latency is not critical. Asterisk separate wall drive asterisk using a separate, faster drive for the wall can improve write throughput, especially on HDDs. 3. Benchmarking tools. Asterisk FIO, Flexible I/O Tester FIO is a low-level disk I/O benchmarking tool. It's useful for understanding the raw I/O performance of your storage device and for simulating different disk access patterns. Asterisk use cases for rocksdb asterisk. Asterisk verifying disk performance asterisk ensure that your disk is performing as expected. Asterisk simulating disk load asterisk generate background disk I/O to simulate a loaded system. Asterisk measuring wall performance asterisk test the performance of the wall directory. Asterisk isolate disk bottlenecks asterisk rule out disk I/O as the primary bottleneck. Asterisk ycsb, Yahoo Cloud Serving Benchmark ycsb is a standardized key-value workload generator. It provides a set of predefined workloads and allows you to customize the workload parameters. Configuring ycsb for rocksdb download ycsb, git clone https://github.com/brianfrankcooper/ycsb.git grave accent. Build ycsb, cd ycsb and mvn clean package. Download and install rocksdb ycsb client, cd ycsb and git clone https://github.com/ycsb/rocksdb grave accent. Copy ycsb rocksdb client to the correct location, cpr rocksdb/roxycsb/jdbc/src/main/java/com/yahoo/ycsb. Create rocksdb ycsb driver using Maven, cd ycsb/jdbc and mvn clean package. Configure the ycsb properties file to use the rocksdb client. Custom benchmarking tools when and why simulating specific application logic ycsb's workloads might not accurately reflect your application's access patterns or data model. Fine-grained control you need very fine-grained control over the workload generation and data collection. Integration with existing systems you want to integrate the benchmarking process directly into your application's code base. Reproducibility ensure repeatability of your tests. db_bench, RocksDB's built-in benchmarking tool. RocksDB includes a built-in benchmarking tool called db_bench. It's a command line tool that can perform basic read and write benchmarks. While useful for quick tests, it's less flexible than ycsb or custom tools. 4. Workload generation and modeling. Understanding workload characteristics read/write ratio the percentage of operations that are reads versus writes, example 90% reads, 10% writes. Key size the size of the keys in bytes, example 16 bytes, 32 bytes, 64 bytes. Value size the size of the values in bytes, example 100 bytes, 1 KB, 10 KB. Access patterns uniform keys are accessed randomly with equal probability. Zipfian a small percentage of keys are accessed much more frequently than the others, simulates hot data. More realistic for many applications. Sequential keys are accessed in sequential order. Latest accesses the latest written keys, simulating a time series or log-based workload. Using ycsb to generate realistic workloads. Example ycsb configuration, rocksdb.properties. Running ycsb. Workload a ycsb workload with 50% reads and 50% writes. Workload, a ycsb workload with 95% reads and 5% writes. Workload, a ycsb workload with 100% reads. Workload, a ycsb workload with 95% reads and 5% inserts. Workload, a ycsb workload with 95% scans and 5% inserts. Creating custom workloads. In C++ or Python, you would simulate the key value operations directly within your code. See examples below. 5. Code examples. Basic rocksdb interaction, C++. FIO configuration example, text. Asterisk Python script for automating benchmarking asterisk. 6. Running benchmarks and collecting data. Asterisk preparing rocksdb asterisk. Asterisk data loading asterisk populate the database with initial data before running performance tests. This simulates a warm cache and realistic data distribution. Use ycsb load phase or write a custom data loading script. Asterisk compaction asterisk force a compaction before benchmarking to ensure that the data is organized and the LSM tree is in a stable state. You can trigger a manual compaction using the rocksdb API. Asterisk while cleanup asterisk consider disabling while for read-only benchmarks to eliminate while overhead. Be careful though, this removes durability guarantees. Asterisk file system asterisk use XFS or ext4 on Linux with no time mount option. Asterisk executing benchmarks asterisk. Asterisk FIO asterisk FIO.job. Asterisk ycsb asterisk dot slash bin slash ycsb run rocksdb workload slash workload a pdb dot url equals slash path slash to slash rocksdb underscore database p operation count equals 10000000 p threads equals 32s. Asterisk custom benchmarks asterisk run your C++ or Python scripts. Asterisk capturing metrics asterisk. Asterisk latency and throughput asterisk ycsb reports these directly. In custom benchmarks, use timers, example std chrono in C++ or time.perf underscore counter in Python, to measure the duration of each operation. Asterisk CPU usage asterisk. Asterisk perf, Linux perf stat e CPU clock instructions cache references cache misses slash your underscore benchmark. Asterisk top or top, Linux slash Mac OS monitor CPU usage in real time. Asterisk disk IO asterisk. Asterisk IO top, Linux monitor disk IO activity per process. Asterisk IOstat, Linux monitor disk IO statistics. Asterisk memory usage asterisk. Asterisk top or top asterisk monitor memory usage. Asterisk vmstat, Linux monitor virtual memory statistics. Asterisk rocksdb statistics API asterisk rocksdb provides an API to access internal statistics. This can provide insights into things like number of SST files, compaction times, and Bloom filter effectiveness. Example code to print rocksdb stats after run. 7. Analyzing results and tuning rocksdb. Asterisk understanding the impact of configuration options asterisk. Asterisk block cache size asterisk a larger block cache can significantly improve read performance, especially for read-heavy workloads. However, it consumes more memory. Asterisk write buffer size asterisk larger write buffers can increase write throughput by buffering writes in memory before flushing to disk. However, it increases memory usage and the risk of data loss if the system crashes. Asterisk compaction settings asterisk compaction settings, example max underscore background underscore compactions, level 0 underscore file underscore number underscore compaction underscore trigger, control the frequency and intensity of compactions. Appropriate settings are crucial for maintaining performance and preventing write stalls. Too many compactions can hurt read performance by consuming I/O resources. Asterisk Bloom filter configuration asterisk Bloom filters can reduce disk reads for non-existent keys, improving read performance. However, they consume memory and can increase write latency. Asterisk compression reduces disk space usage but adds CPU overhead. Choose a compression algorithm that balances compression ratio and CPU cost. Asterisk data visualization asterisk use graphs, example line graphs, bar charts, scatter plots, to visualize the benchmark results. Tools like Matplotlib, Python, or spreadsheet software, example Excel, Google Sheets, are helpful. Asterisk plot latency versus throughput to identify the point at which latency starts to increase significantly as throughput increases. Asterisk plot CPU utilization, disk I/O, and memory usage over time to identify bottlenecks. Asterisk compare the performance of different configurations in bar charts. Asterisk iterative tuning process. Asterisk 1. Establish a baseline. Asterisk run benchmarks with a default configuration. 2. Identify bottlenecks. Asterisk analyze the results to identify the most significant performance bottlenecks. 3. Tune a single parameter. Asterisk change one parameter at a time and rerun the benchmarks. 4. Evaluate the impact. Asterisk determine whether the change improved or degraded performance. 5. Repeat. Asterisk repeat steps 3 and 4 until you achieve the desired performance. 8. Advanced benchmarking techniques. Asterisk benchmarking with different storage devices. Asterisk test rocksdb with SSDs, NVMe drives, and HDDs to understand the impact of storage performance on your application. Asterisk benchmarking with simulated hardware failures. Asterisk use tools to inject latency or errors into the disk I/O path to simulate hardware failures. This can help you assess the robustness of your system. Asterisk benchmarking with concurrent workloads. Asterisk run multiple ycsb clients or custom workload generators concurrently to simulate a high-load environment. This can reveal contention issues and scalability limitations. Asterisk benchmarking different rocksdb versions. Asterisk compare the performance of different rocksdb versions to identify performance improvements or regressions. Asterisk benchmarking in Docker containers. Asterisk package rocksdb and your benchmarking tools into Docker containers to create a consistent and reproducible environment. 9. Facebook's rocksdb usage, lessons learned, hypothetical. Based on the types of workloads Facebook is likely to use rocksdb for and general LSM tree principles. Asterisk scale matters. Asterisk Facebook operates at massive scale. Their rocksdb deployments would need to handle extremely high throughput and large data sets. They are probably using column families a lot. Asterisk read-heavy versus write-heavy optimization. Asterisk different applications within Facebook will have different read/write ratios. They would likely have specialized rocksdb configurations for read-heavy applications, example caching, and write-heavy applications, example social graph updates. Asterisk tiered storage. Asterisk they might use tiered storage to optimize costs. Frequently accessed data could be stored on NVMe drives, while less frequently accessed data could be stored on SSDs or HDDs. rocksdb allows for different levels to be stored on different devices. Asterisk extensive monitoring and automation. Asterisk Facebook would have sophisticated monitoring tools to track rocksdb performance in real time and automated systems to detect and respond to performance issues. Asterisk customizations and patches. Asterisk it is highly likely they have custom patches and modifications to rocksdb to optimize it for their specific workloads and infrastructure. Asterisk compaction tuning. Asterisk Facebook would invest heavily in tuning compaction settings to minimize write amplification and maintain consistent performance. They might use techniques like leveled compaction, universal compaction, or FIFO compaction depending on the application. They might also develop custom compaction strategies. Asterisk compression strategy. Asterisk careful selection of compression algorithm to balance space savings with CPU overhead. They likely use different compression algorithms for different types of data. Asterisk Bloom filter optimization. Asterisk fine-tuning Bloom filter parameters to minimize disk reads without excessive memory overhead. 10. Conclusion. Benchmarking rocksdb is a complex but essential process for ensuring optimal performance. By understanding the key concepts, using the right tools, and carefully analyzing the results, you can tune rocksdb to meet the specific needs of your application. The iterative tuning process, combined with proper understanding of your workloads, is what will give you the best results. Keep in mind to monitor your system using the tools presented above to avoid unexpected bottlenecks. Remember that while I've provided a detailed and comprehensive guide, continuous learning and experimentation are crucial for mastering rocksdb performance optimization.